Roger Young from Tsinghua University proposed a neural network that is functionally equal to a Sajjana fuzzy inference model. He called it an adaptive narrow fuzzy inference system, or ANFIS. The Sajjana fuzzy model type 3 was proposed for a systematic approach to generating fuzzy rules from a given input-output data set. A typical Sajjana fuzzy rule can be expressed in the following form, where x1, x2, xm are input variables. A1, A2, Am are fuzzy sets. Y is either a constant or linear function of the input variables. When y is a constant, we obtained a zero-order Sajjana fuzzy model, in which the consequent of the rule is specified by a singleton. When y is a first-order polynomial, we obtain a first-order Sajjana fuzzy model. ANFIS is normally represented by a 6-layer feed-forward neural network. Such ANFIS architecture that corresponds to the first-order Sajjana fuzzy model. For implicity, we assume that the ANFIS has two inputs x1 and x2 and one output y. Each input is represented by two fuzzy sets and the output by a first-order polynomial. Layer 1 is the input layer. Neurons on this layer simply pass external crisp signal to layer 2. Layer 2 is the fuzzification layer. Neurons in this layer perform fuzzification. In Young's model, fuzzification neurons have a bell activation function. Layer 3 is the rule layer. Each neuron in this layer corresponds to a single Sajjana type fuzzy rule. A rule neuron receives input from the respective fuzzification neurons and calculates the firing strengths of the rule it represents. In ANFIS, the conjunction of the rule incidents is evaluated by the operator product. So, the output of neuron I in layer 3 is obtained as following, where xgi are the inputs and yi is the output of rule neuron I in layer 3. For example, where the value mu1 represents the firing strength or the truth value of rule 1. Layer 4 is the normalization layer. Each neuron in this layer receives inputs from the neurons in this rule layer and calculates the normalized firing strength of a given rule. The normalized firing strength is the ratio of the firing strengths of a given rule to the sum of firing strengths of all rules. It represents the contribution of a given rule to the final result. So, the output of neuron I in layer 4 is determined as following, where xgi is the input from neuron G located in the layer 3 to neuron I in layer 4, and n is the total number of rule neurons. For example, layer 5 is the defuzzification layer. Each neuron in this layer is connected to respective normalization neuron and also receives initial inputs x1 and x2. A defuzzification neuron calculates the weight consequent value of a given rule as following, where xi is the input of the defuzzification neuron I in layer 5, yi is the output of defuzzification neuron I in layer 5. And the case are set of consequent parameters of rule I. Layer 6 is represented by a single summation neuron. This neuron calculates the sum of outputs of all defuzzification neurons and produces the overall ANFIS output Y as following. So, the represented ANFIS is indeed functionally equivalent to a first-order Saggiano-Fuzzy model. It is not necessary to have any prior knowledge of the rule consequent parameters, and ANFIS learns these parameters and tunes membership functions. An ANFIS uses a hybrid learning algorithm that combines the least squares estimator and the gradient descent method. In the ANFIS training algorithm, each epoch is composed from a forward pass and a backward pass. In the forward pass, a training set of input patterns is presented to the ANFIS. Neuron outputs are calculated on the layer-by-layer basis, and rule consequent parameters are indefined. The rule consequent parameters are indefined by the least squares estimator. In the Saggiano style for the inference, an output y is a linear function. So, given the values of membership parameters and a training set of p input-output patterns, we can form p-linear equations in terms of the consequent parameters as given. In the metric notation, we have the following. As soon as the rule consequent parameters are established, we can compute an actual network output vector I and determine the error vector E. In the ANFIS training algorithm suggested by Yang, both antecedent parameters and consequent parameters are optimized. In the forward pass, the consequent parameters are adjusted while the antecedent parameters remain fixed. In the backward pass, the incident parameters are tuned while the consequent parameters are kept fixed. Yang's model and its variants are finding numerous applications, especially in adaptive control. For detailed study adaptive near-fuzzy inference system, we suggest you read lecture notes and apply practice toolbox.